Hello community! Today we're going to talk about an old friend of us, the low-rank adaptation for parameter-efficient fine-tuning in LLM. And there are new insights by MIT. Let's jump right into this. And you might say, what? Parameter-efficient fine-tuning with LoRA? We did this 2 years ago. You have complete playlists and video and everything. What is left to discover? What takes the brain of an MIT researcher to find out about LoRA? Now, let's start at the beginning. If you want to fine-tune a pre-trained LLM, you have at least two possibilities. You can go with the full fine-tuning cycle that is expensive, that takes quite a long time, or you go here with an approximation, with a low-rank adaptation for a parameter-efficient fine-tuning methodology. And the new insight is that both methods here aim to adapt here the pre-trained model now to the new fine-tuning dataset, but they do it in a different way. And this leads to distinct structural and behavioral differences of the model itself. You have to know this if you apply LoRA. So, you remember, full fine-tuning, all the parameters, all the tensors here of the pre-trained LLM during fine-tuning are updated. So this system fully adapts to the task. With a LoRA application, we reduce the number of trainable parameters and all the computational resources needed, so it is faster, it is on less parameters, but there is now a problem with it. Because you remember spectral properties. Those spectral properties are the critical characteristics of a matrix related how it scales and how it rotates vector in space. And in SVD, these properties are represented by the singular values and the singular vectors. And now, in LoRA, as it turns out, the way weight updates are calculated now can amplify all those spectral differences by introducing new singular values and new singular vectors, which can significantly alter now the behavior of our LLM. Those structural differences are quite significant because with LoRA it introduces now new singular vectors. This means new direction in the parameter space that are orthogonal to the singular vectors of the pre-trained model. And this new dimension, they are not just a little bit, but they have large singular values, meaning they have a significant influence on the model behavior. In contrast to LoRA, our other methodology, the full fine-tuning, makes those adjustments to the existing singular vectors of the pre-trained LLM without introducing new orthogonal directions. So this is now a brand new insight, the difference between parameter-efficient fine-tuning with low-rank adaptation and the full fine-tuning job. The structural differences have now behavioral differences of our LLMs. Now we understand why sometimes LoRA models do not work. Because two new insights for getting the pre-trained distribution, those special LoRA models here with those new dimension, they tend to forget more of the information learned during the pre-training phase of the LLM when evaluated outside of this very narrow fine-tuning task. Plus, they are less robust again for continual learning exercises. So those models are less capable of retaining performance on previously learned tasks. Now, these are new insights that are quite massive because this limits now the use of LoRA models. However, in contrast to this, the full fine-tuning models fine-tuned in the full way, retain more of the pre-trained knowledge and exhibit a better performance across different multiple sequential tasks. Now, let me tell you, it is not that the mathematical concept of low-rank adaptation is wrong. What is the most important factor is the rank of the LoRA. So the low-rank LoRA, and this is now where they say, hey, it is below 8, While it is computationally efficient and fast, these models are more prone to developing here this new intruder dimension and the associated drawbacks in the model. Higher rank LoRA, this means a rank starting at 64, increasing the rank reduces now the presence of these strange dimensions, making the model behavior more similar to that of a full fine-tuning model. However, careful, the higher you go with the LoRA rank, the more you have to be careful with the rank stabilization of the model. So let me tell you this, or let me show you this here in our code, Well, here we go with the Hugging Face, a beautiful transformer here from PEFT, parameter efficient fine-tuning. We take here the LoRA configuration, and then we decide here that in the LoRA configuration we have a task type here of R equal 8. Now, what it turns out that this particular choice of the rank is the most important factor for the difference in the behavior of LoRA. So your job is here to find the right R, the right rank parameter. Now, understanding now this rank of a matrix is not as trivial, because what is the rank of a matrix, of a tensor structure? It is simply the maximum number of linear independent rows or columns in the matrix. And this tells us about the dimensionality of the space, of the mathematical space spanned by the matrix. Now, a full rank matrix, the rank is equal to the smallest of its dimension, either the number or the columns, but in a low rank matrix, it is less than the maximum possible rank. So this means that many of its row or columns can be expressed as a linear combination of others. Now there is a mistake that almost everybody makes, especially in the YouTube sector, when they try to explain LoRA, because they mix up the size and the rank. But you, as a subscriber of this channel, you know better, because a size refers to the number of the rows in a column in a matrix. For example, a 512 times 512, you get it, 512 rows, 512 columns. A rank is something completely different. A rank is an intrinsic property indicating how many independent directions or basis vector are needed to span the matrix space. Now, let me give you a very fast overview. If we do here the full fine-tuning update here, and we say our weight structure W0, for example, is our pre-trained model, and then we have a specific task, and we have fine-tuning data sets for this specific task, and we use now the full fine-tuning methodology, we update the weights with a tensor delta W. Now, the size of this is, of course, m times n, and the rank could be up to the minimum of mn, and could be also full rank. So this means all the tensor parameters in our fine-tuned models are updated. And this update can capture all the changes in all the possible direction, given here the complexity of this matrix, of this tensor. So we have a matrix of the size 512 times 512. We have a full rank 512. This means all 512 rows and columns are linearly independent. Now, contrary to this, if we have a low rank matrix, like in LoRA, we have also the matrix size 512 times 512. But the rank is, let's say, 4. So this means now that only 4 rows or 4 columns are linearly independent. And the remaining rows and columns can be expressed as a linear combination of those 4. This means now if we apply this now to the LoRA update, this W0 plus this delta weight, the weights, with LoRA, we have simply a matrix multiplication. Now, if we choose a rank R that is much, much smaller than M, and R is much, much smaller than N, then you know that the resulting W, the size is but at most the rank R. So what does it mean? This means that the update here of our new weight structure is constrained to a subspace of lower dimensionality. This is the critical point, and I will explain this in an example. So if you remember one sentence, if you have the LoRA PEFT methodology with a specific rank R, this means you can only move within a subspace spanned by those R direction if you apply the LoRA methodology to update the weight tensors given here the fine-tuning dataset. So even the room, now that your operator is the same size, the metric, you are still constrained to move within a lower dimensional hyperplane. And this has direct implications in LoRA. This means LoRA reduces hereby the number of trainable parameters, and this is good. This is why we do LoRA. No? We want to have less compute, smaller models, faster models. But having now less trainable parameters, it is now interesting to see that the model now, the new fine-tuned LoRA-specific model, can adjust only along those R direction, R being the rank here, which might not capture all of these beautiful nuances needed for the new task if you choose R in your computer code too small. And you might say, what is too small? And this is next topic. So, if you want to understand this on the next deeper level, we have to talk about the spectral properties in SVD. So you remember from back in school, singular values represent here the scaling factors by which M stretches or compresses here the vectors along the direction of the singular vectors. And the singular vectors, normally U and V, represented here the direction in the input and output space along which this scaling occurs. You know this, singular vectors and singular values here in a singular value decomposition SVD, and you can express here any non-necessarily square matrix M for matrix here exactly with these three elements. U is an M times M orthogonal matrix whose columns are the left singular vectors. Sigma is an M times N diagonal matrix with non-negative real numbers on the diagonal, known as the singular values. They live here in sigma. And V is an N times N orthogonal matrix whose columns are the right singular vectors. Remember this from school? Great. Now, if you're a green grasshopper, you might say, short introduction. Okay, here we go. For the next 2 minutes, if you're not sure, I use here Gemini 1.5 Pro 002 to bring you up to speed. So what we have, the spectral properties of a matrix, of a tensor structure, we have eigenvalues, eigenvectors, and a spectral radius. Please read it carefully, then you're familiar with those properties. If you know this, we can move to the eigenvalue decomposition or eigendecomposition. This means for a square matrix A that can be diagonalized, it can be decomposed in the following way, where we have here a P is a matrix whose columns are the eigenvectors of A. D is the diagonal matrix whose entities are the corresponding eigenvalues. With this eigendecomposition, we already have it. And for real symmetric matrices, we have the spectral theorem. Beautiful. But now with our SVD, our spectral properties and the singular value decomposition, we can now extend this to any matrix, not only to the square one, but even now to the non-square matrix structures and tensor structures. So we have the same idea. We have here a matrix A. We can, if you want, decompose this in this particular way, where we have again 3 other matrices. We have U, M times M, an orthogonal matrix whose columns are now the left singular vectors of A. These are the eigenvectors. Then we have sigma, a rectangular diagonal matrix containing here the singular value sigma of A. And we have here the right singular vectors V. Please note here, for any matrix, we can do now the singular value decomposition. Of course, we will focus here on sigma. This is this middle diagonal matrix in SVD, and this will turn out to be the most important factor if we do LoRA. Again, magnitude, conditional numbers, rank, everything explained for you. And here, in pure mathematics, we already have here the low-rank approximation. So you see, LoRa is not invented for AI. LoRa is just a mathematical methodology that we know of and that we used here for generations. But now we apply it here in a particular way to our fine-tuning of LLMs. And as you see, we have structural consequences. So this means, in contrast to the pre-trained singular vectors that are learned from the large pre-training datasets, LoRa now introduces new dimension learned primarily from the fine-tuned dataset. This is a smaller dataset than the pre-training dataset. And it turns out these new vectors overpower here the pre-trained vectors as seen in the experiment done by MIT so far. We expected this, no? Because we do the fine-tuning for a specific task. And this specific task should be successfully executed. Therefore, if the pre-trained corpora did not include this particular fine-tuned task, of course now with the fine-tuning by LoRa, it must overpower the pre-trained vectors. And MIT has now a deep dive into the analysis. Is LoRa really having the same performance as a full fine-tuned model? And the answer is no. Let me give you here a very simple, this is my example. I want to help you to understand here the complete theory. So we start here with a pre-trained LLM. So we have a pre-training data set, and then we train the model. And let's say suddenly here, these are all our weight tensors. Now, after the training, the pre-trained weight tensors are now here all aligned, and the system learned here all the tasks that were encoded here in the pre-training dataset. And let's say we just want to have one task here go in a straight line. Now we have a new task. The new task is simple, just go a little bit to the right-hand side. So we have now a new fine-tuned dataset for this task, and we fine-tune now our pre-trained LLM exactly on those new tasks with the fine-tuned dataset. And as you can see here in this simplification, our fine-tuned weight tensor for the fully fine-tuned methodology now really alters each and every tensor weight in our LLM. And you see all the tensor are now and say, yeah, let's go a little bit to the right. Now, if the task is now given to a LoRa system, you know that LoRa, watching my videos, normally only changes up between 1 and 3% of the available weight tensors. Otherwise, LoRa would not be so small, so efficient, so fast, because it takes here the main body of our weight structure, and the delta W, the correction terms now for the fine-tuning task, is only done on 1 to 3% of the tensor updates. This means now, in order now to override here the complete, let's say 97% of the tensor weights, imagine LoRa, this adapter now on top of our weight structure, has to have a very powerful vector, a very strong, a real high value in order to override all of those. So you see, in this simple example, we understand if I do the full fine-tuning methodology, the complete system changes. If I do the LoRa methodology, 97% of the system stay the same as in the pre-training phase, and this new task is only learned here on a little tiny adapter, but therefore in this adapter, it has a huge vector that overrides all other vectors. It must have these huge vectors, otherwise this new fine-tuned task is not learned and successfully executed. Great. Now, you know that all the evaluation tell us since 2 years, LoRa performs almost as good as a fully fine-tuned LLM. Well, of course, if the evaluation is exactly on the task, why we fine-tuned. So the fine-tuned task is the object of the fine-tuning itself, and the evaluation is exactly the fine-tuned task. Yes, this huge vector will override here 97% of the other weight tensors, and therefore we will have the same performance as a full fine-tuned version. But, and this is what MIT found, if the evaluation function is now not identical to this simple go a little bit to the right, but if we have now a more generalized evaluation, LoRa falls apart. Now, up until now, I've given you here a simplification. I explained, or I tried to explain the main idea. What is here the deep root cause for this different behavior? Of course, since it was not discovered right until just yesterday when it was published, you understand that we need a little bit of the brain of an MIT researcher and a little bit of mathematics to understand that the publication goes a little bit deeper. For example, here in chapter D, the derivation of the gradients, I just want to show you here. You see here is now the update. And I've given you here the update for the full fine-tuning. So this is here for the full fine-tuning, the formula of our delta weight tensor element. And I've given you here the PEFT LoRA structure. And just looking at the mathematical formulas, you see that there is a difference. Yes, of course. And you see we have our factor R, the rank here, as one of the main deciding factors. So I would recommend, after you watch this video, read the publication. It is really, really precise. It is really a deep dive. You have never seen LoRa in this way before, because they really go down here to a vector level to try to understand why LoRa has some properties or has some characteristics that are not as good as the full fine-tuning. Because there's, of course, a trade-off if we do an approximation between a specific task efficiency and a generalization. So, while LoRa is beautifully computational efficient for a very narrow task that it is fine-tuned on, especially if we go to LoRA ranks, this efficiency comes, of course, at a cost of generalization and the ability to retain the pre-trained knowledge. So this means now for simple tasks where the in-distribution performance is the primary concern, we have one fine-tuning task, and all I want to do with the new system is only this one fine-tuning task. I don't want argumentation, I don't want causality, I don't want extended versions. One task, you do one task, and this is it. Then a low-rank LoRa may be the perfect choice for you. However, if you say, and now my system must also do a little bit more, a little bit different. So for tasks requiring more robust generalization, and maybe you want to have your system that it is a self-learning system, the full fine-tuning methodology, or you use a really high-rank LoRa approximation might be preferable. But you remember here, the higher rank of the LoRa, the bigger this LoRa methodology becomes, the more precise it becomes, the more computational and expensive it becomes, and you come closer and closer here computationally to the full fine-tuning methodology. So where is this sweet spot here in the rank? This is here the critical questions. But don't forget, it depends here on your job, on your task. So, despite achieving a similar performance in the evaluation of specific tasks, we do have different internal changes now to our LLM. Because, as shown by MIT, LoRa introduces new dominant direction in the model parameter space, which can overshadow here the pre-trained knowledge. Of course, remember this huge vector we had here? Yes, it overshadows all the little vectors here that we had down there in the pre-trained knowledge. However, with the full fine-tuning, although it is more expensive, it takes longer, It adjusts here the existing parameters more subtly, preserving the model's pre-trained structure and leading to a better generalization outside of the fine-tuned task. And this is what we are looking for if we want to have here an extended version, if we want maybe have a reasoning, a causal reasoning, a spatial reasoning, and so on. So you see, suddenly LoRA is not as attractive anymore, because we see that the full fine-tuning methodologies, there is some real benefit to go here the full fine-tuning way. Just want to mention, if you go here with LoRA to higher ranks, you have to be careful, because please read this study. For higher ranks with LoRA, you have to apply a stabilization. Otherwise, the system will have its problem in the approximation. So this is a beautiful paper on here, a rank stabilization scaling factor for fine-tuning LLMs with LoRA. Please have a look at it. They give you an explanation why it is necessary that our LoRA adapters have a rank stabilization performed if you go to a rank that is about starting at 64, I would say. So please have a look at this and include it in your calculations. So what is the key takeaway? These new singular vectors that we understand now, they are introduced now by our LoRA methodology. They have a negative impact on the performance of the model, on the generalization of our LLM, and on the knowledge of the pre-training dataset. Our spectral properties of our matrix and tensor structure changes. We have seen this with F3D. Plus, models fine-tuned with the full fine-tuning retain more of the pre-trained knowledge and perform better on tasks outside of the fine-tuning distribution datasets. Great. This is it. This was here the brand new insight from MIT. So you see, even 2 years after LoRA, if you do a deep dive, if you really try to understand the model, you find beautiful explanation that also explain why some of my LoRA models were not able to have the same performance when my task changed just a little bit from the fine-tuned task. Now we understand this is here by the exact way we calculate here our delta weight structures with the parameter-efficient low-rank adaptation methodology. So therefore, if you want to have an LLM that is good in causal reasoning, that is good at performing multiple jobs, it is maybe the best way to go with this new insight from MIT and do and invest in the full fine-tuning job of your LLM. I hope it was interesting. I hope it had some new ideas, and it would be great to see you in my next video.